Hello all, welcome back to Code Hub. Today let us solve the Lead Codes daily challenge and the problem is lexicographically smallest equivalent string. So let us jump into the problem. You are given two strings of the same length S1 and S2 and the string base str. We say S1 of I and S2 or I or equivalent characters when, for example, if S1 is ABC, if S1 is ABC and S2 is C, D, E, then A is equals to C and similarly B is equals to D and similarly C equals to E, and you can see that A equals to C and C equals to E. By according to this problem, the transitivity, symmetry and reflexivity is also to be is true. So what we can say is if A equals to C and C equals to E, then automatically A equals to E is also true. So this is how this transitivities and even symmetry is also true, and also reflexivity is also used as the equivalence relation for this problem. So we want to find the lexicographically smallest string equal to the base str. So let us say, I will give an example to be more clear. So let us take the example 1 itself. As S1 is nothing but Parker and the S2 is nothing but Morris, the equivalence relation, equivalence information for S1 and S2 is nothing but these arrays. This array, how it is formed, as you can see, M and P are equal, so we can just put M and P in one array, and A and O is also equal, so we can just put A and O, and you can see R is equals with R, and K is equals with this R, and R is equals to this yes. So we can just put K, R and S in one array, and also you can see E and I is also equivalent, so we can just put E and I in one array. So now what we have to do is we are given with a string which is known as base str. Base str for this example 1 is nothing but parser. Now we can just form the lexicographically smallest string. How we can form? So for P, what will be the smallest character that that it can replace? It is nothing but I'll just have the 26 letters here: A, B, C, D. Okay, these are the 26 characters. So now for to replace P, is there any smallest character in P? We have only P and M in the which can replace. So for according to this 26 characters, to get a lexicographically smallest string, we just want to put the smallest character in the resultant string. So so M and P, which is the smallest? M is the smallest character according to this equivalence information. And when it comes to A, you can just replace A and O. We can want to put the smallest character, so we just put A. And for R, we can replace all these three characters since R is present in this array. So what is the smallest character in K, R and S? It is obviously a K. You can just see in this 26 characters K and then R and then yes, it comes like this. So K is the smallest character that I can put. When it comes for S, the three characters are K, R and S, and the smallest character which I can put to make a lexicographically smallest is nothing but K. So we can just put K. For E, there are two characters that I can replace, but for E and I, E is the smallest, so I will just put E itself. And for R, there are three characters that I can replace, K, R and S, and as we know that K is the smallest character, we can just put K. And this is what the final string that we got from this base str, and that is the string that we want to return, the lexicographically smallest string. So let us quickly see the intuitive solution or intuitive approach that comes to my mind. What happens here is, first we want to map the characters. Let us say the Parker and Morris. So this is how we are just going to solve this problem, and hope you understand what the question states also. So now let us think of an approach. So let us say the P is mapped with A and P is mapped with M, and M is also mapped with P. Okay, then what it says, A is mapped with O and O is mapped with A. Great. Then for the third character it is R. So let us say R is mapped with R itself. And the fourth character is K. K is mapped with R and R is mapped with K. So we can just put K in this R itself. I'm just forming some information. I'm just collecting the information from this S1 and S2 string. So the fifth character is E and I. So we can just put E is mapped with I and I is mapped with E. So similarly, we can just put R is mapped with S. R is mapped with S and S is mapped with R. So this is the information that we got, which is nothing but the equivalency information that we got from this S1 and S2 string. So let us say we want to form the resultant string with this base str. Let us assume it. So for this P, we can just start from P. The P is the P is the smallest character? No. Is there any other character that is mapped with P? Yes, there is a M which is mapped with P. So we can just go and see for the, and we know that this M is the smallest character than P. So let us go and search for some other characters, smallest characters that are mapped with M. So in M there is only P and P is already visited and P is not a smallest character. So we just not update it. Now by doing some set of function, call or some set of approach, we found that M is the smallest character for this P that can be replaced. So we can just append to my resultant character, which is M. Now let us go for the character A. As you can see in A is the smallest character that we can get, and A is mapped with O, and even in this O is A is mapped. So we can just update A as the smallest character. I will just give the illustration for the third character that will make clear for you. So in R, you can see that R there are three characters that are mapped. So R is itself mapped with R. So R is the smallest character as of now. Then we can just go and see the K. K is also mapped with R. K is the smallest character that we can get compared to R. And then S is also mapped with R, but we don't have but S is greater than K. We just don't want to update. And when doing some function call with K, the K is also K is mapped with R itself. So till now we have got the smallest character that we can get is K. So how we can do this thing in our problem? How can we code this approach? This approach we can just use a DFS traversal by keeping track of the smallest character that we get till now. So this is how we can just form the lexicographically smallest string. We can just do a DFS for every characters that are mapped, and finally we can just return the resultant lexicographically smallest string that we got from this base str. So I will also teach you a unique solution that for this problem, which is nothing but the union find problem after this DFS approach. I'll just live code both the approaches and to make sure that you understand every bit clear. So let us code the approach of DFS, and we will analyze the time complexity later after coding both the approaches. So let us go for the DFS approach. This is the DFS. So what we need is we need to find the equivalency information. How we can form this equivalency information? We can just map every character with every other character, and every other character in the sense if S1 is mapped with S2, then we can just map it. We will be having only lowercase English letters and the constraints are small, which is 26. So what we can do is we can have a two-dimensional array of vector or vector int of size 26. We can just say it as chars. Chars. So this is nothing but a size of 26 and a vector int of 26, and which is initialized to 0 initially. And we want to generate the equivalency information. How we can generate? We can just traverse the string S1 and S2. I'll just take the size of the string and both this s1 and s2 are equal size. So for int I equals to 0, I less than n, I plus plus, what we can do is we can just have two indices, which is a is nothing but s1 of I minus a. We will get some index which is in the range of 0 to 25, 0 to 26. Next is nothing but b is the s2 of I minus a. So now what we can do is we can just map it. How we are going to map it? Chars of a b is equals to 1. 1 denotes that 1 denotes that a and b is mapped. A is mapped with b, and we need to be symmetry. So sorry, it is just chars. And here the symmetric property is also true, so we want to just bidirectionally connect them, which is nothing but b of a is also true. So now we have just created the equivalency information. Now we can just have a resultant string, and we are going to return the resultant string at the end of the day. And how we can form the resultant string? We want to do a DFS for each and every character in the base string. So let us assume we are going to iterate over the character in my base string. By iterating over the base character, what we will be doing is we can have a character initially, character small character in the sense the lexicographically smallest equivalent character that we want to get for that base str of I. So let us say smallest character, and I'm going to update in each DFS call. So get smallest character by DFS. This is the function that I'm going to call, and I need to have a visited vector of size 26 because I should not stuck in infinite loop. So we can have a vector int of size 26 visited, which is initially 0, and I'm going to pass the characters chars array, chars vector to the array, and then the visited array, and I'm going to pass the current character. And we can also have the smallest character as of now is nothing but the ch of my ch, right? This is going to be the smallest character according to me initially, and I can have this as int smallest character. And after doing this recursive DFS call, what I'm going to do is I'm going to append it to my resultant string, and the resultant string is nothing but smallest character plus a, that is going to make it to character. And yeah, okay, now we have the smallest character. Then we are just what we need to do, we are just passing the smallest character as well. We are going to keep it in reference so that it gets affected, the values get affected. Now our whole purpose is to define the function get smallest character by DFS. That is going to be a void function, right? So we can have it as void. And what are the information that I'm passing? I'm passing the characters array. I can have it in reference. Then the visited vector of int visited, and I'm going to have u is the current node in the sense current index, and I'm going to have a smallest character, right? Smallest character, which is going to be reference, passed by reference. Now this recursive DFS call, what it happens is it is going to go for all the path in the sense go to the path which are connected and going to take the smallest character in that path. So if it is already visited, if this visited of u is already true, then we can just return this will be my base case for this DFS call. Then I want to go for all the every characters, that is nothing but 26 characters, right? I equals to 0, I less than 26, I plus plus, and we want to call this get smallest character by DFS, and I'm passing this stats array visitor vector u, not, it is going to be I and the smallest character. and for each and every but when I should update the smallest character, when this is having mapped with u, that is nothing but chars of u I is mapped, then we want to update the smallest character. Smallest character can be updated by minimum of the smallest character comma the current index I, so that we know that it is getting mapped with current index I, so current character I. So we will just pass this current character I, and we will just do a DFS call for the other set of characters that are mapped with I, and the smallest character is also passed, and we want to visit this current node u initially. So that is how we can just do a DFS call. So now let us try to run the code. Before that, I will just give a small dry run. I have just created a 2D array of chars 26 into 26, and I am just taking the equivalency information by the strings s1 and s2, after which I am having a smallest character and a string result, which is going to be returned at the end of the day. And for each and every character in my base str, I have a visited vector of size 26 and initialized to 0, and then the smallest character is initial character now, and I will do a DFS call so that this smallest character get affected. It will get the smallest character in that whole path in the DFS call, and then I will just append it to my resultant string. And in the DFS call, if it is already visited, I will just return to make avoid the infinite loop, and we will visit them, and after visiting we want to go for each and every character if it is mapped. If the current character u is mapped with I, then I will just take the keep track of the smallest character, and I will do the DFS call. This is how we can just write the solve this problem. Let us try to run the code for this problem. Okay, we get some, oh sorry, chars. So I should have kept some other name instead of getting a wrong answer. Great, it gets accepted. Let us submit the code as well, and I will do the complexity analysis at the final after doing the union find approach as well. You will just love that love that approach also. Okay, great, it gets accepted. Hope you like this problem. Now let us solve the same problem using another approach, which is the union find. How we can solve this problem? As we know that for each and every time, for each and every character, we are just doing a DFS call, and we are getting the smallest character in that whole path. Let us say we are having a base str and or, and let us say we are having a equivalency information like all the 26 characters. So for this r, I will just do a DFS for each and every time, and I will just calculate the smallest character in that path. So instead of avoiding that time over time we are doing for each and every character, we can just make use of this union find, which will just keep the parent as the smallest character, and for each and every character in the base str we can just append the parent of that current character in the base str, and that is going to be my lexicographically smallest string that we can get from this base str. So let me say how. Let us say this k and r and s, it is going to be nothing but it is going to be have some group. This KRS is a group, E and I is a group, AO is a group, and MP is a group. So if we have a union find, and we can just map that one group with the smallest character in them while doing a union operation itself, by doing the path compression by in the union find itself, then we can just append the smallest character instead of finding a DFS call each and every time. So now I will just code the DFS class structure, and you will just get the clear idea what I'm just doing. So we can have a class DFS, sorry, class union find. Sorry, I just spelled it as DFS, I guess. So let us have the function, let us have the class DFS. This class, what it is going to have is, it is going to, normally this union find will be having a parent array, a rank array, or a size array, but for this problem we don't want to have a rank array. Instead, what we are going to do is, if this u when doing a union operation, if the u is going to be less than v, that is the u is the smallest character, then we must just make this u to be the parent. So that is like we don't want to make use of this rank array or size array. We can just make use of this parent array alone. So we can have this parent array vector of int parent, and this is going to be the going to keep track of the parent arrays. And inside this union find we just need a constructor union find, and we can just pass the size, but instead we know all it is going to have only lowercase characters of size 26. So we can just resize the parent array of size 26, and for each and every I it is going to be the parent itself. I plus plus parent of I is equals to I. Now we have just declared the constructor. Now what are the other functionalities? We want to find the parent and we want to union them. So we just need these two functions now. So in find parent, this parent is going to take a node u and going to get the parent of this u. So if parent of u is equals to u itself, then the parent itself, then we can just return u. Else if it is having a different parent, we want to do a path compression. Parent of u is nothing but find parent of u. Great, it is as simple as that. That's it. The find parent method is completed. Now we just need another function which is going to do the union for u and v. So this is going to be a void function, and union it takes two parameters, int u and int v, and this u and v we want to do a union. First we want to find the parent of u, then v is equals to find parent of v. And once we have find the parent of u and v, we want to see whether this u and v is same. If both is having the same parent, then we can just return. We don't want to do any union operation. Else we want to union them. How we are going to union them? We are going to make the smallest character to be the representative of that union, of that group. That is, if my u is lesser than v, then what does this denotes? U is the smallest character than v, so make v's parent to be u. Hope you understand by this statement. If u is lesser than v, then parent of v is u. Else parent of u is v. Since u is the smallest character, we just make u has to be the parent for the v, and this is how we can just form this union function, and it is as simple as that. After finding this union, after coding this union find class, we just need to do the other thing. What we can do is we just can eliminate this equivalency information. Instead, what we can do is we can just do a union operation. So this is a union find approach, right? Union find, and it is a great approach. I like solving union find problems. So now we can just eliminate this comment, and we are going to pass this string s1 and s2, and we got the two indices a and b. Now what we can do is we want to union between this a and b. So we can create an object for this union find class, which is nothing but union find dsu, disjoint set union. That is going to be the name of this object, and I'm going to call dsu dot union of this a and b. Now we have done the union operation between these two characters, and we assume that that group is going to contain the smallest character. Once we have the smallest character, what we can do is we are going to iterate over this base str, and while iterating the base str, we don't want this visitor vector, and we don't want this recursive DFS call, and we want to find the smallest character. What is the smallest character? The parent of that group is going to be the smallest character, right? So what we can do is dsu dot find parent of current character minus a. So this gives the parent of this current character, Now we want to now we got this index, smallest character. Now we can just append that smallest character into my resultant, and that is how simple we can just embed this union find approach into this problem. And let us try to run our code. Great, it gets accepted. Hope you see in this screen, and we get the correct answer as well. So let us submit the code now. Great, it gets accepted. Hope you like this. Hope you love this problem by this union find, and I will just give you a small dry run like this. So what we are doing is we have a union class that is having a function find parent and the union or union function, and we are just doing a union between this a and b, which is nothing but s1 of I equal and s2 of I. And we are, while iterating the base str, we are getting the smallest character by the find parent function, find parent method, and we are appending it to my resultant string. So that is how simple by doing this union find approach. So hope you like this problem by these two approaches. Now we can just do a complexity analysis for both the approaches. So as you can see, this runtime is for the DFS approach is 38 millisecond, and for this union find it is just 0 millisecond, and you just need to know the difference between them. Okay, now you may seem like this video is a bit long, but you need to understand the approaches. So that only I have just made the both the approaches and solved this problem. So now this time complexity will be an order of n. Let us say the n will be the size of this string s1 and s2, and we are creating an adjacency matrix with them, and this is going to be an order of m, where m will be the length of the space string, and inside them we are just having a DFS call, and this DFS call will be a 26 into 26 in worst case if it is going to be mapped with each and every character with each and every character. So if A is mapped with each and every character and B is mapped with each and every character, so we just get a reverse time complexity as 26 into 26. So the total time complexity for this approach by DFS is nothing but n plus m plus 26 into 26. So this is the time complexity, and the space complexity will be 26 into 26, and we can say it as some k. If k is equals to 26, we can just say k square, and that is pretty much for this DFS complexity analysis. And let us analyze for the union find as well. And for this union find approach, the complexity analysis will be the time complexity here. Here we are doing a order of n loop, and we are just doing an union operation each and every time. And union and find parent, all this takes a time complexity of 4 alpha according to the union find, and alpha is proven to be a constant by mathematics, and it is known as the inverse Ackermann function also. So this 4 alpha is nothing but it is not going to be large, and it is going to be a constant in our case, and we are just having another loop. This is going to be a size of order of m into another. We are just doing a find parent, right? So we can just say it as log k. So the total time complexity will be n plus m log into log k. So this is very small approach using union find, and compared to DFS, this is the pretty fastest approach and optimized approach for this problem. Hope you like the solution, and let me know in the comments, and if there are any suggestions, let us know, and let us see in tomorrow's LeetCode daily challenge. Until then, bye.